Okay, so the last talk today is by Agnieszka Zelerowicz from the University of Maryland. So a bit far from here. Anyway, you're very welcome. Hello. And the title of her talk is Large Intersection Classes for Pointwise Emergence.
Thank you very much. I would like to take a moment to thank the organizers for the invitation. I really wish I could be in Bannerus right now with all of you, but I'm very happy that the organizers made it possible for me to attend the conference and give a talk remotely. So I would like to talk about my joint work with Yushi Nakano, where we analyzed the pointwise emergence and introduced some large intersection classes to study points with emergence. Okay, so let me get right to it. So what I'm considering in my talk is are points which are irregular. And that means that if you take a point and you take a delta measure at this point, and then you move the point under the dynamics, and you push this delta measure together with the dynamics, and you average this measure, you look at those averages along trajectory. I'm looking at points for which this average does not converge. So those points are called irregular. And first of all, in a certain way, this set is very small or even negligible, because by the Berger-ergodic theorem, we know that for every invariant measure and almost every point with respect to this invariant measure, the averages do converge. So I'm talking about the set of zero measure with respect to any invariant measure. So in a way, this set is very small, and ergodic theory does not see this set. However, in many ways, this set can be large, and it's been proven to be large for many dynamical systems. So let me just mention some results. So since we know that the set is a set of measures zero with respect to all invariant measures, the next tool that we can use to measure the size of this set is just measure the dimension of the set. And in fact, for many dynamical systems, the dimension of this set is full. So it's been known that this set has full Hausdorff dimension, and in fact has full entropy for the following systems. So for topologically mixing subshifts of finite type, this is a result by Berger and Schmeling. And in fact, this is exactly the setting in which we've been working. So Berger and Schmeling show that for topologically mixing subshifts of finite type, the set of irregular points has full Hausdorff dimension and full entropy. This has been also shown for some other dynamical systems. So for graph-directed Markov systems, it's a result by Farm-Persson. For continuous maps with specification, it's the result by Chen, Cooper, and Shu, which was later extended to continuous maps with almost specification by Thompson. All right. So, okay. So now that we are talking about the points which are irregular, so the Berger averages do not converge, we can ask how irregular those points really are. So we can look at the set of accumulation points of those averages. So I'm going to denote this set by A of X. So for every point which is irregular, we can look at the set of accumulation points of those Berger averages, and we may ask how big this set really is. So a priori, just from knowing that the averages do not converge, it would be enough that this set AX only has points, right? This would be enough to have a point which is irregular. However, this never really happens because the averages, like, they kind of change little by little, right? So you can imagine that if you have two measures in the set, two different measures, which both are accumulation points of those averages, then also this set AX must also contain a certain path connecting those two measures, right? So we can already imagine that this set, unless it's just one point, then we already know that this set must be rather big. So we want to measure the set, and the tool that allows us to measure the set, it's called pointwise emergence. That was defined by Kiriki, Nakano, and Soma. And this is a pointwise version of metric emergence, which was introduced by Berger. So what is a pointwise emergence? So we pick a scale epsilon, and pretty much we ask how many epsilon balls it takes to cover our set AX, right? So how many balls we need to cover the set AX on a scale epsilon. So of course, as the scale gets smaller, we will need more balls to cover the set. And so this is a result by Kiriki, Nakano, and Soma that claims that if a point is irregular, then the pointwise emergence is infinite, right? And this is because, as I already mentioned, if we have two distinct measures which are in the set of accumulation points, then there must also be a path connecting those two measures, which is also in the set of accumulation points, right? So if we have the whole path, then of course it takes infinitely many tiny balls to cover the set. I mean, the number goes to infinity with epsilon. All right. So this is the first observation. But now, so the next thing that we may need to ask is how fast this number n grows. Okay, so we already know that for a point which is irregular, this number grows to infinity. So the next natural step is to study how fast this number goes to infinity. And in fact, we can. So in this talk, I'm going to look at this set of points for which this number goes to infinity at a super polynomial speed. And I'm going to call those points points with high emergence. Is there a question? No. All right. Yeah, so I'm going to look at the set of points for which this thing here is true. So at any scale, pretty much like you cannot rescale this emergence to get something finite, right? At any rescaling, it's always infinity. So it's super polynomial. Okay, so the first question is, can we even find points for which this emergence is super polynomial, is that high? And the answer is positive. And in fact, Kiriki, Nakano, and Soma, they constructed a set of points with high emergence. And in fact, it's already known that the set is very large because it's a residual subset. So they studied the full shift and they constructed a residual subset such that all the points have high emergence. And it was, in fact, it was conjectured by Berger that for a typical dynamics, the metric emergence is high. So this is something to be expected. Okay, so in my talk, I'm exactly looking. So we are considering shifts of finite type, and we are looking at set of points with high emergence, and we want to study how large the set is. So let me just state our result. This is our main result. If we have a topologically mixing subshift of finite type, then the set of points with high emergence has full topological entropy and full dimension. So this was the result by Schmeling for that the set of irregular points has full topological entropy and full Hausdorff dimension. And we actually extended to not just irregular points, but the points with high emergence. And in fact, our approach is rather general and can be used to study other dimensional characteristics, not just Hausdorff dimension. So kind of for free, we obtain other things. As an example is pressure. So if we have a Hölder continuous function, and we look at the topological pressure of this function, we can compare the topological pressure on the whole space and on the set of high emergence. And in fact, we say that the set of points with high emergence is going to have full pressure. So I don't know if there are any thermodynamics people in the audience. In case you are not familiar with the notion of the pressure, then don't worry, this is just another dimensional characteristic that we get for this set. And in fact, we get more. Our result is more general. And I will state the general version of our theorem at the end of my talk. But before that, I have to define some notions. Okay, so in fact, we prove this theorem in our paper in two different ways. One way is to actually construct a set of points with high emergence such that it has full topological entropy and full Hausdorff dimension. And I will not talk about this direct approach. Maybe Yushi will mention it tomorrow in his talk. But I want to talk about another way of proving this theorem, which is a little bit more general. It can be used to study other dimensional characteristics of the set with high emergence, but also it gives a way to study other sets. So yeah, it's just a little bit more general. Okay, so in order to talk about this approach, I have to define many objects that I will be working with, and I hope I won't. I hope it will not be too abstract and too confusing. Okay, so I already said that we are going to study different dimensional characteristics. What I mean by that is that we are working with the notion of dimension, which is like very general and abstract. It's called Kara-Theodore dimension. So it's a generalization of a Hausdorff dimension. So let me just talk about this. Let me first introduce this. So, okay, so in order to introduce the Kara-Theodore dimension, which is a generalization of Hausdorff dimension structure, let me just recall how we construct Hausdorff, how we introduce Hausdorff dimension. So what are the ingredients that are needed in order to define Hausdorff dimension? So in order to define Hausdorff dimension, we need open sets, right? And then if we want to, and we define so-called Hausdorff outer measure. So we pick a parameter alpha between 0 and infinity, and for each parameter alpha, we define the corresponding outer measure, which is given by this formula. So let me go over this formula. What this formula does, we take a set that we want to measure, we cover it with open sets of some small diameter. Diameter must be smaller than epsilon. And then we add up the diameters raised to the power alpha. Okay? And then we take the limit as the size of the cover goes to 0, right? So we cover it by open sets with smaller and smaller diameter. And this defines an outer measure. It's a Borel outer measure. How this measure behaves, you can already see that if you take alpha, which is too small, it is very close to 0, then you can see that this outer measure will be always infinite, right? On the other hand, if you take alpha, which is very big, then you will get always 0, right? So the way this measure, as this outer measure behaves with the parameter alpha, there's actually a jump, right? So there is a critical value of alpha such that there will be a jump from infinity to 0. So from all the values of alpha which are smaller than this critical value, the measure is infinite. And for all the values which are bigger than this critical value, the measure is 0. So we have only one critical value when possibly this measure may be positive and finite. However, this is, in this case, at this critical value, pretty much anything can happen. Okay, and this critical value, it's exactly the Hausdorff dimension. So this is how we define Hausdorff dimension of a set. Okay, so I want to generalize this whole construction and define different dimension, not necessarily Hausdorff dimension, but something else in exactly this way, using those ingredients. So what I'm talking about, it's a Kara-Teodori dimension structure, which was first introduced by Kara-Teodori, but then later generalized by Pessin. And so how does this generalization go? So okay, so what you see now is the definition of a Hausdorff outer measure. Now I'm going to be changing this formula to obtain Kara-Teodori outer measure. So we are going to do the following changes. Okay, so in order to obtain Kara-Teodori outer measure, first of all, our parameter alpha does not necessarily have to be a non-negative number. It can be negative, right? It can be any real number. Let's take the first modification. But then there are others. So first of all, we define a family of admissible sets that we are going to use as our covers. So for the Hausdorff dimension, those were open sets, but in our general construction, those can be any sets. Just we define a collection of admissible sets. And then in this formula of the outer measure, instead of the diameter raised to the power of alpha, we introduce some set function eta, and we have this function eta raised to the power alpha. But then also we multiply by another function, which is psi. So in this formula, we have eta, it is a replacement for diameter, but we also multiply everything by some function psi. And then we require that, so then we also have this other function, which is psi, and which is gonna serve as the size of the cover, right? So again, in Hausdorff dimension structure, this was just the diameter of a set, and we require that we use covers by open sets with small diameter. Here we are going to cover by admissible sets of small sizes, but the size is defined by some function psi. It doesn't have to be diameter. It's just something else that we define to measure a size of our set. Okay, so this is it. And now, in order to actually make sense out of it and produce dimension out of this, we need some requirement on the two functions eta and psi. So imagine we defined three set functions, eta, psi, and psi. And I just want to point out that there are no requirements on the function psi. The function psi can be anything, but we do have some conditions on the function eta and psi. So those are the conditions. We need the function eta and psi to be 0 at an empty set and strictly positive otherwise. And we need some continuity condition that says that eta, the value of eta is small if the size is small. And the last condition says that we have to be able to cover our space by admissible set of arbitrarily small diameter. So that's, of course, needed to define this outer measure. And those are the only three conditions that we need to introduce a Kara-Teodori dimension structure. Okay, so here, so we define this new outer measure, which is the Teodor outer measure, defined this way, and turns out that this function behaves the same way as that this measure behaves the same way as the Hausdorff outer measure, in a sense that it also has a critical value for which the value jumps from infinity to 0. And it's because we have this jump, we can call this critical value the Teodor dimension of our set. So this is how we define it, right? So depending on what you want to study, you can define this Teodor structure differently and obtain something else as Teodor dimension. So for an example, as an example of this, I'm not going to give any actual formulas, but I just want to mention that as applications of that, as examples of that dimension, we obtain entropy as a Teodor dimension. We also obtain pressure as a Teodor dimension. We just have to define Teodor structure differently, and we obtain different things as dimensions. So that way we obtain entropy, pressure, and of course Hausdorff dimension is clearly an example of a Teodor structure as well. All right. So now, how we use it to prove our theorem. So I'm not going to talk about any particular Teodor structures, but we are only considering Teodor structures for which the collection of admissible sets is just the cylinders. So we are on the full shift. We have the cylinders, okay, and those are our admissible sets that we used in the covers. And then in our constructions, we modified the Teodor measure a little bit, and we defined this new outer measure, which is this capital M, which is the only modification that we did here. We did not require to cover, so if we measure our set, we do not require the covers to be small. So in this definition, the function psi no longer plays any role. So the function psi, which was the size of a set, no longer appears in this definition. It just does not exist. We just use the covers, which give the infimum of this sum here. So those measures may not be as nice, that they have less chance to be Borel, but what is nice about those measures is that they are always finite. Right, so those outer measures, because we do not require the sizes to be small, we can just take one big cylinder and use it to cover our set. So those measures are always finite. Okay. So yeah, so let me just list some relations between those two measures. So the original measure, the small m, was the Teodor outer measure that defined the dimension. The next theorem says that we pretty much could use this capital M to define the dimension. Because this is what happens for those functions. So they both define outer measures, not necessarily Borel, but outer measures. This capital M, this measure is always smaller than the small m, and in fact it's always finite. And the way it behaves is if we take the value of alpha, the t, greater than the dimension, then the both measures are 0. However, at t less than the dimension, this capital M, this measure is positive and finite, while this original Teodor outer measure is always infinite for t less than the dimension. And at the dimension, pretty much anything can happen. The small m can be 0 or can be n infinite. The capital M is always finite. So if the small m is positive, then the big M is always also positive. However, if small m is 0, then they are both 0. Okay, so those are the relations. So in fact, in our constructions, we used this function capital M a lot. So let me. Okay. So here I listed some conditions that we needed for our approach to work. I don't want to go over them because they are just very technical. So the thing is, they're all very natural. They hold. It's pretty much automatic that they're all satisfied for Hausdorff dimension. So if our function q was a diameter, which is the case for the Hausdorff dimension, then all those conditions are pretty much obvious. However, since we are working with general Karat-Hölder structure, we don't really have a lot of information about this function q, so we need to impose some conditions for our result to be true. So those are just those conditions. And okay, and now we define a class of sets that we will use to study Karat-Hölder dimension of the set with high emergence. So here I should point out that our approach was inspired by the work of Farm and Person. They studied Hausdorff dimension of certain irregular points, and they introduced this class of sets. They did it for Hausdorff dimension. And what is nice, if you define this, they proved that if you define the class of sets this way, then they have very nice properties. They have countable intersections. They're closed under countable intersections, and the dimension of any set in this class is greater than the value G. So it can be used to study Hausdorff dimension of many sets. And we extended this idea to just general Karat-Hölder dimension. So we introduced a class of sets corresponding to arbitrary Karat-Hölder dimension, and we proved the similar result as he proved, that this class is closed under countable intersection, and all those sets have large Karat-Hölder dimension. So the class of sets that we consider here are G delta sets, such that if I intersect this set with any cylinder, then this measure MT, which is defined in the Karat-Hölder construction, this measure must be the same, right? So as we intersect our set with any cylinder, the measure should not decrease, should be the same. Okay, so those are the sets that we consider. And automatically, well, not automatically, we proved that the following about this class of sets, that if our Karat-Hölder structure satisfies the conditions that I just listed, then this class is closed under countable intersections, and the Karat-Hölder dimension of any set in this class is at least T. So this is a very useful tool on its own to study various dimensional characteristics of sets, not only sets with high emergence, but just any sets. And the fact that they are closed under countable intersections is also very useful. Okay, so let's see how we can obtain our result from here. Okay, so now we are back to points with high emergence. So we are looking at irregular points. And let me remind you that by AX, I denote the set of accumulation points of Birkhoff averages. And so now let's fix a probability measure. Actually, I mean an invariant measure. I should say that we need this measure to be invariant. And let's denote two sets. Let's denote by E of mu all the points such that mu is in the measure mu is in the set of accumulation points of the Birkhoff average. And another set of points, G of mu, those are generic points with respect to this measure. So those are all the points for which the Birkhoff averages actually converge to our measure. So those are all those points in the set G, they are actually regular. They are generic points with respect to this measure. And they have full measure, right? With respect to this measure, this is a full measure set. So in particular, this set has dimension the same as the dimension of our measure. Okay, so what we were able to prove with Yushi is that under the conditions on the Karatodori structure that I listed, for any measure, for any invariant measure, the set of points E of mu, so those are all the points for which our measure is in the set of accumulation points. This set belongs to this class GT, so this class that I just previously introduced. For every t, as long as t is strictly smaller than the Karatodori dimension of the set of regular points with respect to this measure. So in particular, if you take any t which is smaller than the dimension of your measure, then the set E mu is in this class GT, right? So, which means that the set E mu has, already we know it has dimension greater, it has dimension at least t. Okay, so this is the first thing that we showed. And now we can explore the fact that if we are in this class of sets, and those sets are closed under countable intersections. So now we can take countably many measures and then intersect those sets E mu with each other, and we will not leave that class. So as a corollary, we obtain that if we have a sequence of measures, right? So the J here is a infinite sequence of measures, and we consider a simplex which is spanned by those measures, and we consider the set of points for which this whole simplex is in the set of accumulation points. And we show that the dimension of this set is at least as big as the smallest of the dimensions of the measures. Okay, so this is one thing. Another thing is immediately from knowing that we have a point which is in this infinite sequence, infinite simplex, then the emergence is high for that point. Okay, so this is exactly what we are going to use to show that the dimension of points with high emergence is high. All right, so clearly, if you have infinitely many measures and that they're all ergodic, linearly independent, if you have a point that such that the whole simplex of those measures is contained in the set of accumulation points, then clearly this point must have high emergence. And yeah, and this is the result that we prove. So this is like the general version of the theorem that I stated at the beginning of my talk. So the theorem says that we have a topologically mixing subshift of finite type. We look at points with high pointwise emergence, and then we introduce a Karatodori structure. As long as this Karatodori structure satisfies those technical conditions C1, C4 that we listed, but we also need additional condition. We also need that there exists a sequence of measures such that the Karatodori dimensions of those measures converge to the Karatodori dimension of the whole space. If we have that, then we can conclude that the set of points with high emergence has full Karatodori dimension. Of course, this condition C5 is needed because our construction, our Karatodori structure is can be so general. In general, it's not even known if this Caratodori structure satisfies variational principle. It may not. So this condition is definitely required. We need to have a sequence of distinct ergodic measures whose Caratodori dimensions converge to the dimension of the whole space. If we have that, then the set of points with high emergence, and those are really the points which contain the whole simplex spanned by those measures, then the set of those points has full Caratodori dimension. So,
Agnieszka, like, why do you need a sequence of measure here? Why do you need a sequence of measure? Why can't you take just one measure, which satisfies C5? You could take just one measure. You could take a constant sequence of measure which satisfies this, like in the order of quantificator you have.
Because if we just, so we use the fact that we have infinitely many measures because we want to produce high emergence. So we want to have points such that, those Birkhoff averages, they kind of travel between all those measures, right? So the set of accumulation points contains all those measures, contains all this whole simplex by those measures. And because of that, we can conclude that those points have high emergence, right? So this is how we prove high emergence. Otherwise, if we just had one measure, I mean, we can only look at points which have this measure in the set of accumulation points, and we cannot conclude that those points have high emergence. Yeah.
Could you have, in the last equation, could you have the maximum of the dimension, instead of DC of X, the maximum of the dimension of Caratodori dimension of the invariant measure?
I mean, yeah, in general, if we didn't have, if we didn't have condition C5, right, which means we probably do not have variational principle, then all we could obtain from our approach, looking at the points with high emergence, we could obtain the dimension, which is exactly the supremum of the dimensions of measure. But again, we have to be careful because we need the whole sequence of measures, right, that converge to the supremum, and they have to be different because we have to make sure that we do have this infinite simplex and that we don't have just one measure. But if we do have a sequence of measures, right, then which are distinct, then we could conclude that the dimension of points with high emergence is the supremum of those dimensions. Yes.
But I don't understand why linearly independent is sufficient, because you could have a simplex which is infinite dimensional, but which is very well approximated by a finite dimensional submanifold, for instance. Like how do you get to avoid the fact that you want those measures to be a little like far to be included in a submanifold? I mean, you can imagine, like, you understand what I mean? Like, how do you get at some point in this proof of this theorem to get that the set of like the set of this measure, like the convex rule of this measure, is far to be included in a submanifold of finite dimension?
I'm not sure I understand the question.
Like, I mean, like you could imagine that the mu of L converges extremely fast to a measure which is invariant. And in this case, I don't see how you get that the dimension is infinite.
Right. So what we do, we exploit this countable intersection property of the sets in this class that we defined. So this is why what we do, we intersect countably many measures. So we make sure that if we have a point, it has all those measures in the set of accumulation points. And we do not decrease dimension as we take all those intersections. So this is kind of, we have to exploit this countable intersection property.
Okay. Thank you.
Thank you.
It's okay. So more questions, comments?
Yushi finish his slide. You have one more slide?
Yeah.
Ah, this is the end.
I do have one more slide. Thank you. Slide, thank you.
So questions?
So can you recast your contribution with respect to those already exist in your work, Baradira, Pessin, can you learn maybe that can get learned and somebody else did something like this?
Yeah.
Like your main contribution is to say that it's not only just historical behavior, but you've got a lot of measure. Is it like?
Right. Yes. Yeah, so many results were obtained for irregular points, but as far as I know, the notion of emergence itself is rather new, and there weren't any results in that direction about the size of points with high emergence.
And is there any hope to get to use your work to construct example for which the reference measure is smooth in a manifold for smooth dynamical system?
I hope so. Yes, we would have to like use the horseshoes, right? It's kind of method like approximation by horseshoes, and then use our result about shifts of finite type to say something about diffeomorphisms. I think that something in that direction we should be able to do.
Questions? So in the beginning you mentioned a conjecture of Pierre, right? So maybe you can explain if your results can say something about this conjecture.
About conjecture by Pierre?
Pierre Berger, I think, yes. And you explained it, right? The conjecture, if I am not wrong.
There was a conjecture. I just thought it was.
Or it's not Pierre Berger, it's different Berger.
Okay, so yeah, so we actually discussed that with Yushi, and if our approach, if our result gives any contribution or any information about metric emergence, and at this point we do not know. Like on one hand, we are using measures and we are measuring points with high emergence. However, those measures, they are not very useful. Because the measure, we define two different outer measures, right? And the small measure m, this measure is always infinite for if we take the critical value, if we take the value less than the dimension. Right? So our constructions, our estimates, we always assume that we take t, which is smaller than the dimension, and then we consider the corresponding measures. So the measure small m, it's always infinite for the measure less than the dimension. So it's not very useful to study metric emergence. On the other hand, this measure capital M, which is always finite, but the way we define it, we kind of lose the fact that this measure is Borel. So this measure is no longer Borel. So none of those measures are very useful to talk about metric emergence, unfortunately. We were discussing it with Yushi if we can produce maybe some other measure somehow that would be somehow natural and useful. But at this point, we don't know the answer.
So if there are no other questions, let's thank her again.